All right. This is our first projectile motion example. So we're going to take all the things we learned yesterday about vectors and accelerations and which way they point, and we're going to apply it to this problem right here. All right. So first thing I asked you guys to do was think about our first step in this problem. So the tennis ball is thrown at a 50-degree angle. What was our first step, Sergio?
Oh, you gotta find the components.
Got to find the components. Good. So we need to find the x and the y component of what? The tennis ball being thrown, right? So, okay, two green markers. So here's our x component, right? Right? And here's our y component, correct? Thank you, Wesley. So vx, vy, right? Right, does that make sense, guys? Everybody draw that picture? Maybe not the dotted line out, but did we at least draw the triangle? Yeah. Okay. What's our initial velocity? 8. So 8 is v, right?
8 is the hypotenuse.
Okay. It's the hypotenuse, perfect. And we know from earlier that vx equals v. Remember that Sokotoa stuff? You can just remember this equation, right? Where's the 8 go in?
Theta.
The v.
Or, yeah.
What's theta?
Theta is the angle.
The angle, right? Which is what?
50.
50. And what a mode do we have in our calculator? Degrees, good. So do 8 cosine 50, and what do we get?
5.14. Wait.
Yep.
I got 7.7.
It's not in
Make sure you're in degrees. Hit the mode button. So 5.14 and 7.7. Who's right? 5.14? Put 5.1x. That would make sense. Okay. Does that make sense, guys?
Yeah.
Okay. Now to find Vy. We know Vy equals V, not cosine, but
Sine.
sine theta. Right? So V is still 8 and theta is still
50.
50.
Will there ever be equations with more than an angle?
What is it?
6.1.
6.12? Yeah. Thank you, Maria. Sergio, what's the question?
Will there ever be questions where there's more than one angle?
More than one angle. Probably not. Not for us. There are questions like that, but not for us. All right. All right. We could have a wind direction and all that stuff, but we're not going to get into that. All right. By writing these down, what are we assuming about our directions? Which ways are positive? Okay, we're assuming that up is positive and to the right is positive. We're assuming both those are positive, aren't we? Right? Does that make sense? Up and right are positive? Okay. Are there any questions about how I found those? Okay. Now, there's a couple things they want us to find. They want us to figure out how far away the tennis ball lands, right? They want us to find that spot right there, right? Right, guys?
Yeah.
Okay. This distance is an x distance or a y distance?
X.
An x distance. Okay. They want us to find this distance. I'll put a little x next to it so you know. Okay. They also want us to find, so that's part A, isn't it? Maybe instead of writing an x, I should write an A there. They want us to find that distance right there. That's part A, right? What else do they want us to find? The maximum height. That's which part? Okay. That's right here in the middle of the curve. Part B, they want us to find the maximum height, don't they? Right? And what do they want us to do for part C? Okay. The time of this maximum height. That's what they want us to do for part C. All right. So I'll just put a little C next to it, a little circle around this, and put C next to it. All right. Because I'm going to take this whole right part down in a second. Okay. So does that make sense, guys?
Yeah.
Now, do I have all the information I need off of the picture right here? The tennis ball is thrown 50-degree angle. Got that.
You don't have time.
8 meters per second. I don't have time, do I?
No.
Okay, so we might figure that out. All right. All right. Anything else? Think I got it all? Got all my information?
Yeah.
Okay. Now, another thing I asked you to do, okay, was start thinking about all the equations we might know from one-dimensional kinematics, right? So we have these two equations that we know. Are there any other one-dimensional kinematics equations that we know? Okay, is that right? Good. Velocity equals v naught plus acceleration times time, right? Any other ones? Velocity equals distance over time, right? Right? Isn't that the same as doing this? Oh, not that. Because this isn't distance, this is change in distance, right? Yeah, so I call it delta d over delta t. Or I could rewrite it like this. Right? Right? The second one? Well, delta d is d minus d naught, right? Right, Sergio? Okay. So I multiply both sides by t, right? So then I have vt equals delta d, right? This is d minus d naught. Add that to both sides. Same equation I have right there, just write it in a different order. Does that make sense? Yeah? Okay. Victor, you got another one?
Acceleration equals delta v over delta t.
Okay. So acceleration equals delta v over delta t. That one is basically this equation, isn't it? For the same reason that these two are the same equation. Right? Same solving. Okay. Anything else? Probably a good idea. And I'll move these over to our equation spot here in a little bit. Okay. What about that one? Is that a good one? Is one of those equations? Okay. So those are all of our equations. Those are all of our equations.
Including those up there, what's that v?
Yep. Those that flip diagram theorem using the x and y components, right? And then we got the two equations we used to break into the components. Got these two equations, right? All right. Any questions about that? Yeah.
Is the beginning of that thing, the angle, the same as it? Just backwards.
Yes, because symmetry. They'll come in at the beginning as well. Good question. Okay. Any other questions? All right. Now I'm going to leave those equations there. I'm going to kind of over here. We're kind of on the side a little bit. We'll go right. All right. Now there's some certain steps to solving this problem. Okay. Or yes, steps / rules. Okay. I guess you can call them both steps and rules. Right. The first step is to make a what? We already drew a picture, right? Now we need to make a list. Okay? So first step, we already drew a picture, so draw a picture and make a list. Now, will one list work? No. One list will not work. Why won't one list work? There's two dimensions, right? So we got to draw a picture, make a list for good the x and y direction. Yes, Kim.
Is this for this problem only? Is it for overall problem?
This steps all the problems. Okay. So if you want to like put these in a margin somewhere, maybe a good idea. I told you that ahead of time. I'm sorry. Okay. So let's make a list. What are some things we know? in the x direction? What do we know? Yep, I picked PIC. Draw a pie, good. Okay. Draw a picture. A JPEG. A GIF, whatever you want to call it. A GIF. Is it a GIF?
GIF is peanut butter.
No, it's not. All right. So, draw x and y direction. What are some things we know in the x direction? Mikir, got anything we know in the x direction? Yeah, what do we know? Okay, what is that? It's the bottom thing, which is it's an x component of the velocity, right? So, is that initial, final, or what? Okay, it's the same thing, right? Because in the x direction, we know acceleration is 0. Right? So that means that this right here, 5.14, that is our velocity in the x direction. Right? That is our velocity in the x direction. Brings us to our first rule. First rule / step. I guess I think they just need to come up with make guidelines or something. I don't know. Just some different title for the step / rules, kind of leave a little bit to the imagination. All right. First rule / step is or second rule / step is there is no acceleration in the x direction. Okay, my voice got a little louder there. Okay? Because I don't know why, Emmett, but students always want to do an acceleration in the x direction. Okay, maybe we should take notes. Maybe we should turn this thing around. Okay? Get something out. Okay, go with paper. Alright, stop sitting here just talking to Shelby, distracting me. Okay, so there is no acceleration in the x direction. Hey. I have a candygram? Oh, okay. Who's it for? Paige? She's actually down in the library. Thank you, Lexi and Jamie. Alright. There is no acceleration in the x direction. Let me say it again. There is no acceleration in the x direction. Okay. You want to say it with me?
Ever.
Okay. Right. Ever. Unless you count air resistance. Okay. Ready? 1, 2, 3.
There is no acceleration in the x direction.
Good. I know. Just trying to make you think I was going to help out. All right. I don't know why, but students will always want to make the acceleration in the x direction negative 9.8. Okay, does that make sense? Think about it physically, conceptually. Does that make sense that there's a negative 9.8 acceleration in the x direction? No. Are there any forces acting on this projectile as it goes this way? Are there any x forces?
Yes.
No, we're ignoring air resistance. Are there any x forces? No. So there's no x forces. Is there an acceleration? Kevin? No. F net equals ma, right? There's no net force. There's no acceleration, right? Now, which direction do we have a net force?
Why?
The y direction, right? What's the net force acting on the ball? What's the net force acting on the ball? What's the only force acting on the ball? Gravity. Gravity leads to an acceleration of what? 9.8, which direction, up or down? Down. Okay. There is an acceleration. Actually, we're just going to shorten this up because I know you guys don't like long sentences. We'll just put this.
Gravity's pushing down.
A equals 9.8 meters per second squared down in the y direction. Okay. And that 9.8 meters per second squared down, that is what?
I have a question.
Yes.
X always have a velocity.
Depends on how we shoot the ball.
Depends on what?
If I shoot the ball straight up, is there next velocity?
Oh,
No. Okay. Just like if I shoot the ball completely horizontal, is there y velocity? No. Okay. So, in the y direction, we know acceleration equals Now, if we call up positive, that 9.8 meters per second squared needs to be negative, right? Because it is downward. It all depends on which way you call the positive direction. Michael.
You said that 9.8 meters per second squared is negative. Will it ever be positive?
If you call down positive, then it'll be positive. Okay? Good question. All right. In the x direction, in part A, we want to find this distance, right? Right? So we don't know D. Right? Do we know something about position in the x direction? Do we know the initial position in the x direction? Because we start right here, don't we? So we start at 0, right? So we know D naught is 0 meters. Right? Is there anything else we know in the x direction? No. You sure?
Yes.
Doesn't the ball eventually hit the ground?
Yeah.
When the ball hits the ground, what happens? Hits the ground and it stops moving, right? So when the ball hits the ground and stops moving, what's its velocity? 0. So can we write V naught or V final 0?
Yeah.
No!
Why?
You can't do that.
Why?
Okay? Another thing students always like to do. They like to say, well, the ball's on the ground at the end, so both these final velocities are 0. Right? Well, once it hits the ground, now a force is applied. It's no longer projectile motion. Okay? Once the ball hits the ground stops it. How does the ground stop it?
Friction.
Friction, normal forces. It applies a force to the ball, right? So we no longer have a projectile motion. So when we're doing problems like this, the final velocity occurs at the very moment right before the tennis ball hits the ground. That's where the final velocity occurs. Okay. Now we know in the x direction, there's no change in our velocity. Okay. In the y direction, there's a change in our velocity. Okay. But we cannot say the final velocity is 0 because you're looking at the moment right before it hits the ground.
So it'd be the same, it'd be 5.14.
Yeah, velocity is 5.14 the whole time. In the x direction. Okay? So don't let yourself say, oh, the ball hit the ground, final velocity is 0, easy, got it, done. Doesn't work that way. Okay? Okay, instant right before it hits the ground. Okay. So we want to find position here. We know D naught is 0, we know V is 5.14, we know A is 0, right? Take a quick look at our equations. Is there any equation that we can fill in all the variables for? Why don't you erase these delta ones, because I think they get a little confusing this time of year. That's alright, you can write it down. I'll help you remember that there's the same thing. Okay. Is there any of those equations that we can populate everything? Number 5. But that's just V equals V, isn't it? Okay. Or sorry, not number 5. Number 6. Number 6 just ends up being V equals V, right? Acceleration 0. Right? So we end up with V final equals V initial. That'd be a lot of fun. Almost. Okay. Okay, what did you say earlier? I thought you said number 6, but you really said number 5. So would 5 be a useful equation? Okay. There's no acceleration, right? 5 is the one where we have no acceleration, correct? All these other ones have an A value, don't they? There's no acceleration in the x direction, so why would we want to use a more complicated equation? So what equation are we going to use for this x direction?
Oh.
We're going to use which one? 5. Okay. We're going to be using this equation. Okay. We're going to be using D equals VT plus D naught. Okay. Now, Kevin, if we start to populate this equation, this D is the one we want to find, right? Right? V is 5.14. Correct? Do we know T? No. Do we know D naught? Yeah. So if we populate this equation, we get 0. How many unknowns do we have? 2. How many equations do we need then? How many equations do we need? How many equations do we need?
I say 1.
We need 2 equations, won't we? 2 equations, 2 unknowns, right? So we need to find what still? Time. Now there's something special about the time, isn't there? What's the special thing about the time? Has no direction, right? Which means if I can find time in the y direction, right? Won't that apply to the x direction? Yeah. So, last step / rule guideline thing. Okay. Time is a scalar. Right? Time is a scalar, right? So what does that mean?
Has no direction.
Has no direction. So that means time it takes in the x direction equals the time it takes in the y. Right? Time in the x equals time in the y. So that means we need to use the y direction to find what?
X. Right?
We use the y direction to find the... We use the y direction to find the time. Okay. So, let's make a list of what we know in the y direction. What are some things we know? Say acceleration thing of 9.8. Do we know initial position?
Yep.
Yeah, what's initial position? 0. Now, if I'm hitting this spot right here, do we know final position as well? Yeah, what's final position? 0. Right. It's so close to the ground that we can call it 0. Unless we need 0.00000000000000001. That's like picos or femtos. I don't know which one it is. Lost count of my zeros. Right. So it's almost 0. Anything else we know? Velocity. What's velocity? Right? Anything else we know? That's let's get deep. Anything else we know? What do we want to find? Time. Right? So, do we have enough to fill in one of our equations? Which equation can we fill in? Acceleration equals velocity over time. We're going to use that one, though. That means we need to know what about the... What do we need to know, Victor? Okay. This velocity, is this initial or final? Initial. It's going to change, right? If we're going to use acceleration equals velocity over time, change velocity over change in time, we need to know the final velocity, right? Is the final velocity 0 because it hits the ground? No. Good. You guys remembered. Okay. The final velocity is not 0 because it hit the ground. Right? So we do not have a final velocity to use acceleration with change in velocity or change in time. Okay, we don't have that. Right? So what equation can I populate with what I know? Three. We can populate 3, can't we? Alright, so all these I think you guys probably have written down by now. Alright. We can populate 3. D equals 1/2 AT squared plus V naught T plus D. We can figure this one out, can't we? Right? Okay. Oh, forgot my knot. So let's plug in what we know. Final velocity is. Sorry, final position. 0. 1/2 A is negative 9.8. T is. We're trying to find. V naught is 6.12 T. D naught is 0. Some of you are saying, oh crap, I don't want to do a quadratic formula. Who's taking that right now? Okay, alright. Let's see if we have to. 1/2 times negative 9.8, what's that? Over here, negative. Right? Right? Does that make sense? I don't need to add the 0 anymore because I'm going to add 0 to anything else to go right back. Now, what's one obvious solution here? Did we know an obvious solution? What's 1 time? What is it? And 0, right? If both our t's are 0, will this equal 0? Yeah. So basically what that tells us is that when we launched the ball, we were where? On the ground. Okay? So that's one solution to this, because if you have a squared, you always have two solutions. Right? That's one of the solutions. Okay? Let's find the other one. So what should we do? We could factor, right? That's one route you could take. If you factor, you'd end up with this. 0 equals t negative 4.9 t, oh, not t squared, plus 6.12, right? Set the factors equal to 0, find your answer. Works just fine. Okay? We all might not be at the factoring stage yet, so let's do this without factoring. Okay. Should I keep my t's together, or should you think I should separate them? What do you guys think?
Yes.
Yes, do something, right? All right, I'm actually going to separate my t's. So I'm going to add 4.9 t squared to both sides. The math teacher me is saying, why are you getting things on the other side? Right, why are we getting variables on two sides? But sometimes you have to do it. Now, why do you think I do that? So we not just factor, we can do a c. Cancel a t, right? So now this t cancels with one of these t's, right? Correct? So now we have 4.9 t equals 6.12. What do we do now? Divide by 4.9. What does the time equal? What is it? Man, I think I've done the problem before. Good planning by Mr. Branch. 1.25 seconds. So that means the ball is on the ground here, okay? Is on the ground at a time of 0, right? On the ground at a time of 0 and a time of 1.25. So this occurs at t equals 0. This occurs at 1.25, right? Right? Now I want to figure out how far it traveled here, right? So how long did it travel with a velocity of 5.14 meters per second before hitting the ground? How long? 1.25 seconds, right? Since it took 1.25 seconds for the tennis ball to go up and come back down, right? That means it has 1.25 seconds to go from where we started to that point right there. Does that make sense? So that means that this time right here is what? 1.25. Plug that in over there. Position equals 5.14 times 1.25. And what does that equal? 6.425? Yep. And the units are So that. Part A. Boom! All done. Yep. But is it difficult work? Kinda? I think the hardest part is making your two lists. Okay? If you can make your lists, then you can figure it out. Okay? Now typically, Sergio, you're going to be using the y direction to find the time, plugging the time into the x direction. Alright? Alright. Part B. We want to know the height at this spot right here, don't we? Right? Now there's some cool thing about symmetry that tells us that this height occurs at what time? If it takes 1.25 for the whole trip, right? We know this maximum height occurs at what time? Half of that 1.25, right? Okay. So this maximum height, so really the answer to part C equals time for max height equals 1.25 divided by 2, right? 1.25 divided by 2 is 0.625. So we know at 0.625 seconds, the tennis ball is right there at its maximum height. Does that make sense? Does that make sense, guys? So can we figure out that position? We know time, right? We know initial velocity, right? We know initial position. We know acceleration, right? Right? So can we figure this out? For part B, we should probably make a new y list. So on your page, on your notes, if you want to write part B, we can make a new y list. Okay, I know we did C out of order. Sometimes physics teachers like to do that. No, that's part C. Because C says what time are they at the maximum height. We had to do it out of order. Right? We didn't have to, but it's the easiest way is to do it out of order. Okay? So to find part B, what I would do is I'd make a new y list. Right? So let's take this y list that we have right here and let's edit it for part B. Okay. So, is acceleration still 9.8? Is initial position still 0? Is final position 0? No. This is what we want to find, right? That's this spot right here. We want to find this spot right here. That is our final position. So this final position, we don't know now.
We know it's going to be greater than 0.
We know it'll be greater than 0. Okay. Doesn't really narrow down the possibilities though. Okay. Do we know time? Yeah. Time was the half of 1.25, right? Because time max height equals half of total time, right? So half of 1.25, which we said was 0.625. Okay. Right? Now, what equation do you think we should use? Probably this one again, right? Right? Because we have basically all the same ones. We just switched that. Now we know t, but we don't know our final position. So we're going to use that equation again. Let's plug in what we know. So d we're trying to find 1/2 of negative 9.8 times 0.625 squared plus 6.12 times 0.625 plus 0. Right? So can you guys figure this out now? Yeah, you can do it all in one step in your calculator if you're smart with your parentheses, right? 1/2 times negative 9.8, don't forget your negative, times 0.625 squared, plus 6.12 times 0.625, She looks funny, so it's bugging me.
Equals.
What is it? 1.91? You agree with Victor? Mister says, yeah, anyone else? 1.91? So that means the tennis ball reaches a height of 1.91. So part A took a lot of steps, right? But then part B and C ended up being kind of easy. Are there any questions?